What's up, guys? Today we're going to be looking at objective 5.5, which is determining types of bonds. So what we're going to ask ourselves, our essential question today is, how can we look at two elements bonded together and determine what type of bond they have? Now, if you use your brains and think back to 5.1, the lab you guys did and the notes we took, talked about three different types of bonds. We talked about ionic, and then we talked about covalent, and then two different types of bonds that are covalent, so polar and nonpolar. And what we really looked at, we looked at physical properties and how to tell the difference in physical properties of these bonds. But now that you guys know about valence electrons and bonds and how those go, we can really dig into the main differences between these types of bonds and how to tell what they are on the electron level. So just to review, ionic bonds are a bond between a metal and a non-metal. So let's look at our periodic table again. A metal is just anything below these stair steps. So zinc could be a metal, sodium plus chlorine, because anything above these stair steps are non-metals. So sodium plus a non-metal, chlorine, that's going to be an ionic bond. A covalent bond is two non-metals. So anything above these stair steps over here combined. Carbon plus oxygen, nitrogen plus chlorine, that's going to be a covalent bond. So what happens electron-wise in an ionic bond is the metal gives away, or really it loses, electrons to the non-metal. So let's look at sodium and chlorine. Remember that sodium has one valence electron and chlorine has 7. So sodium really gives that valence electron to chlorine. Chlorine takes it away. They don't share it, it just takes it. That's what happens in an ionic bond. Sodium is just giving its electron to chlorine. And if we remember about ionic bonds, they also conduct electricity when they're dissolved into a solution. They conduct electricity when they're dissolved in a solution because they break into two different parts. They break into their metal component, they break into their non-metal. So when they break, it conducts electricity because the metal part conducts the electricity through the solution. Covalent bonds don't conduct electricity because they have no metal. So ionic bonds, when they break into the metal, and that conducts electricity. And just remember, as a review, ionic bonds have high melting points and high boiling points because those bonds are so strong. It takes so much energy to break them. Now let's move on to covalent. Remember how I said with ionic bonds, the metal gives the electron to the non-metal? In covalent bonds, that's not really the case. They more share the electrons. Now how they share the electrons is the main difference between polar and nonpolar. So nonpolar bonds, think like two kindergartners. Two kindergartners share a toy for 10 minutes. If they share it equally, they share it for 5 and 5. That's a nonpolar bond. Nonpolar bonds share the electrons equally, back and forth, equally shared. Polar bonds is like that bully kindergartner plus the nice kindergartner that doesn't want to say anything. So the bully holds it for 9 minutes, the nice kid holds it for a minute. We're still sharing it. We're just sharing it very unequally. That's a polar bond. So how do we look at these things, these elements, and decide if it's nonpolar or a polar bond? Well, you guys remember the 5.4, our last objective, we talked about electronegativities. Such a beautiful word. You guys don't have to write this chart down. You guys will be given it whenever you need it, but this is a chart of electronegativities. Electronegativities can be put in a number form, and that's just what we did here. So remember, electronegativities go up as you go across a period, so that's why you see these numbers getting bigger. And remember that electronegativity is just the measure of how much protons in the nucleus pull on electrons in the outside of the atom. So let's look at a nonpolar bond. A nonpolar bond is anything with electronegativity difference of 0.5 or less. So 0.5. So if it's 0.5 or less, it's a nonpolar bond. Now what do I mean by 0.5 or less? Well, let's look at carbon and boron. If we had a compound where carbon and boron are bonded together, it's going to be, we can do this. We can do 2.5 minus 2.0, which is boron's electronegativity, equals 0.5. And this is just subtracting these two electronegativities. That's all I did. Now, since it's 0.5 or less, then we see that anytime carbon and boron are bonded together, it's going to be a non-polar bond. So that's how you decide if it's non-polar. How do you decide if it's polar? Well, anything above 0.5, so like between 0.6 and 2.0 is going to be a polar bond. So if you subtract the numbers, you get between 0.6 and 2.0, that's polar. Okay, so how do we do this? How do we know this? Well, you guys might have heard that water is polar before. So water is H2O, so 2 hydrogens and an oxygen. So what we're going to do is we're just going to subtract 2.1 from oxygen's electronegativity, which is 3.5. So 3.5 minus 2.1, which is hydrogen's electronegativity, equals 1.4. So that 1.4 is between 0.6 and 2.0. That makes a bond between hydrogen and oxygen always polar. So what that means is oxygen is tugging on those electrons a lot more and sharing them very unequally with hydrogen. It has a lot of those electrons more around it, closer to it than hydrogen does. So I'm gonna let you guys try it really quick. And yes, you're actually gonna try it. If I were to give you a bond between carbon and fluorine, what kind of bond is it? Is it gonna be nonpolar or polar? Try it, yeah, try it. Okay, so hopefully you guys started the math a little bit, got it done. But let's do it for everybody. So fluorine has a 4.0, carbon has 2.5, and that equals 1.5. Okay, so is 1.5, does that equal 0.5 or less? No, so we know it's not nonpolar. Then between 0.6 and 2.0, yeah, so we know it's polar. Anything above 2.0, you're really getting in that ionic territory. So that's, but don't worry about that, we're not really going to ask you that. Just know that between 0.6 and 2.0 is polar. So just for review, ionic, giving electrons away, not really sharing them, just giving them. Covalent, shares electrons. Nonpolar, shares equally. And any electronegativities, 0.5 or less of a difference, nonpolar, boom. Polar, any electronegativity difference between 0.6 and 2.0 is polar, and those share very unequally. And that's the way the cookie crumbles on differences between bonds.